What we're going to do in this video is introduce the fundamental language of modern mathematics, set theory and set operation. Sets are essentially the mathematical study of collections of objects, and they give us a common way to organize and analyze information, whether we are working in logic, probability, computer science, or statistics. Now, I have a few examples of collections written here on our screen, like counting numbers less than 10, or the set of all horses with 6 legs. Before we dive into the definitions, I encourage you to pause the video and think about whether each of these is well defined. Meaning, can you absolutely decide if a specific object belongs in that group or not? Alright, let's think about this together. A set is a well-defined collection of distinct objects, which are called elements. You can think of it like a club membership. An object either belongs to the club or it doesn't. If A is a set, denoted by an uppercase letter, and X is an element, denoted by a lowercase letter, we write as such, which is read as X is an element of A, or X belongs to A. If X is not an element of A, we write as such, which is read as X is not an element of A, or X does not belong to A. For instance, let's say set A is defined as such. Then we can say E is an element of A, and 3 is not an element of A. In set theory, we have a few special types of sets to keep in mind for our walkthrough. The first one is empty set or null set, denoted by such symbol phi or an empty set. An empty set is a set with no member. In our previous example, the statement, the set of all horses with 6 legs, since we cannot find any horse with 6 legs, the set will be empty set. The second one is universal set, denoted by U. A universal set is the set containing every element relevant to a particular discussion or problem. It serves as the reference set from which all other sets are formed, meaning every set under consideration is a subset of the universal set. Any well-defined set can be either a finite set or an infinite set. A finite set is a set that contains a limited number of elements. In other words, its elements can be counted completely, and the counting process eventually comes to an end. An example is the set of vowels in the English alphabet. An infinite set is a set that contains an unlimited number of elements. No matter how long you continue counting its elements, the process never ends. An example is the set of all counting numbers. Let's look at some examples and classify them as either finite or infinite sets. The first example is the set of odd natural numbers. This set starts with 1 and continues without end. Since there is no last element, it is an infinite set. The second example is the set of natural numbers less than 1 million. This set contains the natural numbers from 1 up to 999,999. Even though it contains a very large number of elements, every element can be counted, so it is a finite set. The third example is the set of all real numbers between 0 and 1, including both 0 and 1. Although the set has clear boundaries, there are infinitely many real numbers between 0 and 1. Therefore, this is an infinite set. In the listing method, infinite sets are usually expressed using partial listing, since it is impossible to list all of their elements. Finite sets, on the other hand, can be expressed using either complete listing or partial listing. Now let's discuss the concepts of subset and proper subset. A subset, denoted by subset or equal to, is defined as a set in which every element of one set is also an element of another set. A proper subset, denoted by strict subset, is slightly different. If A is a proper subset of B, then every element of A is also an element of B, but B contains at least one element that is not in A. In other words, A and B cannot be equal. Remember that every set is a subset of itself, and the empty set is a subset of every set. However, no set is a proper subset of itself, because a proper subset must always be strictly smaller than the set that contains it. Now that we've covered these basic types of sets, let's move on to a graphical representation of set relationships called the Venn diagram. A Venn diagram is a visual tool used to represent sets and the relationships between them. We represent the universal set as a large rectangle and individual sets as circles inside it, since every set under consideration is a subset of the universal set. Venn diagrams also provide a convenient way to illustrate concepts such as subsets and proper subsets, as shown. Now that we see basic concepts of set theory, let's walk through our 5 core set operations together. The first one is union, denoted as shown. When we say A union B, it is the set of all elements in A or B or both. Symbolically, we say it is a set of all x such that x is an element of A or x is an element of B. In a Venn diagram, we shade everything inside both circles. The second operation is intersection, denoted as such. Intersection consists the common elements that are in both A and B simultaneously. We write it as it is a set of all x such that x is an element of A and B. Visually, this is just that overlapping shape in the middle, showing elements that is found in both sets. The third one is relative difference, or relative complement, expressed as such. When we say A complement B, which is written as such, it includes elements that are in A but not in B. Logic-wise, it's written as it is a set of all x such that x is an element of A but not an element of B. On our screen, it looks like a crescent moon shape where B has been bitten out of A. It shows the area denoting only a member that are found in A, but not in B. Sometimes relative complement expression is also read as the relative complement of B in A, or A minus B, simply. The other complement is absolute complement, expressed with prime. When we say A complement, it is everything in the universal set that is not in A. We define it as a set of all x such that x is an element of universal set but not an element of A. You simply shade everything outside the circle A when illustrating it using Venn diagram. The last operation is symmetric difference, expressed by triangle symbol. When we say A symmetric difference B, it is the set of elements found in either A or B, but not both. We define it as A complement B union B complement A. In set builder method, we can define it a set of all x such that x is an element of A but not A, or x is an element of B but not A. Or in other way, we can express it as A union B complement A intersection B. In Venn diagram, it is illustrated as such. Let's see these operations in an example. Here we have 2 sets. Set A has members including all factors of 12 in natural number, and set B has members of even natural numbers less than 10. Since these sets are expressed in a set builder method, we express them in listing method for ease of understanding. Therefore, set A becomes 1, 2, 3, 4, 6, 12, and set B becomes 2, 4, 6, 8. First, let's see union and intersection of the 2 sets. A union B becomes 1, 2, 3, 4, 6, 8, 12, and A intersection B becomes 2, 4, 6. Now, when we move to the concept of complement, the absolute complement of A and B will be expressed in set builder method, since partial listing might confuse some. Because when we list A complement as 5, 7, 8, 9, 10, 11, 13, 14, etc., one cannot be sure the randomness of the members. Therefore, we say A complement is a set of all natural number x such that x is different from 1, 2, 3, 4, 6, 12. Same goes for B complement as well. Note that the set of natural number is our universal set. Relative complement will be defined as A complement B will be 1, 3, 12, which are elements in A but not in B. And B complement A will be a set containing the number 8. The final operation will be symmetric difference of A and B, which is a set containing 1, 3, 8, 12, which is similar with B symmetric difference A. A union B A intersection B and symmetric difference of A and B are all commutative, but relative complement between two sets is not commutative unless the two sets are the same. If the two sets are the same, then their relative complement will be empty set. The other point is a double complement of any set is the set itself. De Morgan's law also applies here between union and intersection, the same as we'd seen in logic, where union and intersection being as disjunction and conjunction, whereas complement acts as negation. The other concept in set theory is the concept of cardinality. Let's briefly see what cardinality is. Cardinality, which is denoted as such, is just a fancy word for the number of elements in a set. Taking the previous sets, for example, set A has a cardinality of 6, meaning it has 6 elements, whereas set B has 4. We use this to count elements in unions and intersections, ensuring we don't double count those overlapping members in the middle. When two sets have equal cardinality, then they are said to be equivalent, and when two sets have similar members, then they are said to be equal. Here are other common properties with set cardinality shown on the screen. To grasp the idea on set cardinality, here we have a word problem, for example. The question says, in a university, 150 students were surveyed about the languages they study. The finding says 95 students study English, 80 students study French, and 30 students study both English and French. Now, find how many students study at least one of the two languages, how many students study only English, how many students study only French, how many students study neither English nor French. First, let's extract our given in a set expression. Before doing that, let's say E for students who study English and F for students who study French. Then, the cardinality of English studying students is 95, and for French studying students is 80. For students who study both, we express them as the cardinality of E intersection F, which is 30, and 150 will be the cardinality of our universal set. Then, to solve question number 1, which asks the number of students who study at least one language, we use the cardinality of E union F. Cardinality of E union F is the summation of both cardinality minus intersection. When we substitute the given number, we'll find 145 for an answer. Question number 2 requires us to find the number of students who only study English. This is solved by finding the cardinality of set complement. For only English studying students, it is E complement F, and is found by subtracting intersection from E cardinality, and for French only, we subtract the intersection from F cardinality as shown here. The final question is the number of students who study neither language. This question asks the cardinality of E union F complement, which can be found by subtracting the cardinality of E union F from the universal set, which is 150 minus 145, which we find from the first question, and the answer will be 5. I hope this example further clarifies the concept of cardinality. Set theory is the building block for almost everything else you'll learn in math and science. We've covered elements, membership, Venn diagrams, and the 5 major operations. And we're done. If this walkthrough helped you feel more confident with sets, hit that subscribe button to join our community here at Rimetric Walkthrough. Thanks for watching and see ya!